Hello, we are going to be talking about sequences. They are super useful. Now, just to start, let's go over the definition here. So a sequence is, definitionally, it's a function whose domain, and remember that means the numbers that you're plugging in, whose domain is the set of positive integers. Okay, so let's discuss what that means real quick. So remember, positive just means bigger than zero. Integers means that it's sort of like whole numbers. Okay, the set of integers is all the negatives, all the positives, and zero, no fractions or anything like that. Okay, and they have to be positive. So really, we're just talking about the natural numbers. So that means that the input of a sequence is going to be a natural number. Okay, or sometimes we call them the counting numbers. So like 1, 2, 3, 4, 5, 6, 2, 3. And we talked about in class that we represent that set using a double bar n. Okay, now in functionality, a sequence is just a list of numbers. But to give some meaning to a sequence, it's going to be a function. Okay, so first example, I am given this function right here, and I'm asked to write the first 6 terms of the sequence and then do a little graph. Right, so all I'm asking you to do is literally, we're going to plug in 1. And I'm plugging 1 in for n. So I'm going to plug in 1, I get 1 over 1, which is 1. This is my first term. Okay? My second term is when I'm going to plug in 2. Okay? So you always start with 1 and then you count upwards. So when I plug in 2, I get 1/2. If I plug in 3, I get a third. If I plug in 4, I get a fourth. If I plug in 5, I get a fifth. And last but not least, when I plug in 6, I get a sixth. Okay, so not too bad. You're literally just plugging in 1 and then you're counting upwards, and those are the numbers that you plug in. And if we were to graph this, then we would get, well, let's just see. So the only numbers I plugged in were 1 through 6. So 1, 2, 3, 4, 5, 6. Okay, and the numbers that I got were between 1 and 1/6. So I'll call this 1. This is about a half. That's about a third. And maybe a fourth, the fifth, the sixth, third. Okay, so the numbers I got were starting up way up there, and then they progressively got smaller and smaller and smaller, but the distance between them started to sort of level out. Okay, so we end up with sort of a curve here. And later we're going to learn this something called the harmonic series, but for now, it just is what it is. It's the reciprocal function. Okay, so if you take a look at what we just did, hey, you'll notice that the number that I plugged in is corresponding with its place in the sequence. Okay, so what I mean by that is, let's go down here. Okay, so what I mean by that is my first term was 1 because I had 1 over 1. And my second term was 1/2. My third term was a third, a fourth, and so on, right? Well, when I plugged in 1, that was my first term. When I plugged in 2, that was my second term. When I plugged in 3, that was my third term. And when I plugged in 4, that was my fourth term. Okay, so whatever number you're plugging in for your variable, in this case n, but it could be any letter, okay, whatever number I plug in for my variable corresponds with its place in the sequence. So when I plugged in 1, that was my first term. When I plugged in 2, that was my second term. Okay, and a lot of times the way that I represent that is with a subscript. Okay, now the letter might change that we use. Usually we use an A, but usually we use a subscript, and that just means a small letter to the bottom right. Okay, so A1 would represent my first term, A2 would represent my second term, A sub 3, and then A sub 4. And that's typically what we use for sequences. We usually use A, but it doesn't really matter. A could change. Sometimes you use U, we could use B, it doesn't really matter. Okay, so we're going to do the same thing, slightly different notation this time. Okay, I'm given what looks to be a slightly more complicated sequence, and I'm going to write the first 6 terms and then plot, just like we just did. Okay, so I want to find b sub 1. Okay, well, to find b sub 1, again, what I'm doing is I'm just taking this number 1 and I'm plugging it in from my variable. So I have negative 1 to the 1 plus 1 times 2 over 1. Okay, well, negative 1 to the 1 plus 1 is negative 1 squared times 2. Negative 1 squared is 1 times 2 is just 2. Okay, so b sub 1 is 2. Okay, and you're going to go through the same process over and over again. So if we do the same thing, we plug in 2, this time we'll get negative 1. If we plug in 3, this time we get 2/3. If we plug in 4, we get negative 1/2. If we plug in 5, we get 2/5. And if we plug in 6, we get negative 1/3. Okay, so more or less the same thing. All you're doing is you're taking this set of natural numbers, okay, 1, 2, 3, 4, 5, the counting numbers. You take those, you plug them into your function as many times as you need to, you get a list, and that's your sequence. Okay, now one thing you might notice is that the sign that I got for each of my terms kept alternating. And that's something important to notice, and that's what this negative 1 to the n plus 1 does. The whole reason why that's there is it doesn't actually affect the value of my number, but it affects the sign. So this negative 1 to the n plus 1, this makes it so that each of my terms keeps alternating in sign. That's something to notice. And that makes my graph look real wonky. Okay, so if I were to graph this, I go as high as positive 2 and as low as negative 1. Okay, and I went 6. So 1, 2, 3, 4, 5, 6. Okay, so my first number, when I plugged in 1, I got 2. So that's all the way up here. When I plugged in my 2, my second number, I got negative 1. When I plugged in 3, I got 2/3. When I plugged in 4, I got negative 1/2. When I plugged in 5, I got 2/5. When I plugged in 6, I got negative 1/3. Okay, so kind of like in my first example, the numbers are trending towards the x-axis. Okay, it's getting the distance between the point and the x-axis is getting smaller and smaller, but because it alternated sign, it ended up like zigzagging across the x-axis in this one. Okay, let's move on. All right, let's learn about factorials. Okay, so factorials are used a lot in probability. The factorial is defined as the following. Okay, if I have some variable n, which is greater than or equal to 0. Okay, so n just represents a number, it has to be positive. And if that number is an integer, and remember integer just means like sort of a whole number, then there's a couple things that's true. Okay, but first of all, we'll just say this. That means that n factorial is equal to n times n minus 1 times n minus 2 times, and then you just keep going until you get all the way to the bottom. So times 3 times 2 times 1. Okay, you stop multiplying when you get to 1. There's a couple of exceptions to this rule. We define 0 factorial to be 1. We define 1 factorial to be 1. And I'm just going to write this rule here because it's really useful, but you can also define n factorial as n times n minus 1 factorial. And we'll explore what all of this means. So if you're a little bit confused, that's totally fine. We'll do an example. Okay, so I'm asking you to write 7 factorial in 3 different ways and then compute it. Okay, so comparing what I'm given to my definition, 7 is my n value, okay, and 7 is greater than or equal to 0, and it is an integer, so it works. Okay, so 7 is what I am sort of plugging into my rule here. Okay, so what I'm telling you factorial is you take your number, you multiply the number right before it, so, or you subtract 1, so 7 times 6, and then you keep going. So times 5, times 4, times 3, times 2, and then you stop when you get to times 1. Okay, and that's what 7 factorial is definitionally. Okay, so you take your n value, whatever you're starting at, and you keep decreasing in value by 1 until you get all the way to 1, and then you stop. That's what factorial is. And if you were to compute this, you get 50/40. right? But I asked you to write this in 3 different ways, and this is where this rule comes in. So notice that 7 factorial is, all of these numbers multiplied together. But notice that if I just took this part, this is 6 times 5 times 4 times 3 times 2 times 1. This is the same thing as 6 factorial. So I could sort of stop short and write this as 7 times 6 factorial, and that would be the same thing. Okay, and that's what this rule means, is that n factorial equals n times n minus 1 factorial. You can stop short at any time. Right? And if I were to ignore that and look at just here, this is the same thing as 5 factorial. So I could rewrite 7 factorial as 7 times 6 times 5 factorial. And that would be the same thing, because remember, 6 factorial just means 6 times 5 times 4 times 3 times 1. 5 factorial just means 5 times 4 times 3 times 2 times 1. And so really all of these are the same thing. We're just sort of abbreviating the statement using this exclamation mark. That's all that that does. It condenses a whole bunch of numbers into one singular statement. Right? But all 3 of these are exactly the same thing. Really all 4 of these, including this top here. Okay, all of these mean the same thing. And we're just multiplying a descending order of numbers until you get to 1. Okay, last bit. There are 2 types of sequences that we work with, recursive and iterative. Recursive we see a lot in programming, we see iterative a lot in programming as well, but iterative functions are more like what you've been dealing with in math for forever, whereas recursive functions you've probably seen in programming. A recursive sequence relies on preceding terms. Okay, what I mean by that is, well, another way of putting that is you need previous terms. So if I gave you a sequence that is recursive and you wanted to find, say, the second term, well, you would need the first term in order to do that. Okay, whereas with an iterative function, it does not require any previous terms. You could, if I gave you an iterative sequence, you could find the 100th term without needing anything else. Okay, you could just find that. Whereas with a recursive sequence, if you wanted to find a 100th term, you'd need the 99th term, which means you need the 98th term, which means you need the 97th term, which means you need all of the terms starting from the first one in order to find the 100th. Right, so let's just do walk through an example of this really quick. So let's write the first 5 terms of this mess right here. Okay, well, we define this as the first term. So remember, this subscript tells me the place of my number. Okay, so like where it is in the sequence. So u sub 1 means this is my first term. Okay, so my first term is 1. My second term is 1. Okay, so that means if I was to write this out as a list, it would go 1, 1, and then I need 3 more because I want to find the first 5 terms of my sequence. Okay, so this was u sub 1, this is u sub 2. I need to find u sub 3, u sub 4, and u sub 5. Okay, well, thankfully I'm given this statement right here. It says that u sub n equals u sub n minus 2 plus u sub n minus 1. So if I wanted to find my third term, which is u sub 3, then I'm just going to take 3 and plug it in for n, because that is my variable. That's the value of my variable here. Right, well, we just have to do a little bit of arithmetic. So 3 minus 2 is 1, and 3 minus 1 is 2. Right, so what this is telling me is that if I want to find the third term, I have to add the first and the second terms together, okay, which is good because I know what those are. It's 1 plus 1. Okay, so my third term is 2. It's the sum of my 2 previous terms. That's what this is telling me. All right, let's do it again. So I want to find the fourth term. Okay, well, if I simplify this, this is telling me I have to add my second term and my third term together. Okay, well, my second term is 1. My third term I just found is 2. So my fourth term is 3. Right, so you'll notice that what this is asking me to do is add together or find the sum of my previous two terms. Okay, so in order to find my third term, sorry, I had to add my first and second, so the previous two. In order to find the fourth term, I had to add the second and third. So in order to find my fifth term, you could probably guess, I have to add the third and the fourth terms together. Right, and this is 2 plus 3, which is 5. So I get 5 as my use of 5. And I don't know if you've heard of this, hopefully you have, but this is called the Fibonacci sequence, where you add the two previous terms together to get the next one, and then you keep going. Hey, that's an example of a recursive sequence, the Fibonacci sequence. All right, that's it for this video. I will see y'all later.